Okay, I suggest to get started. So hi everyone, it's a pleasure to host former Monash students, now Dr. Amelia Fraser McKelvie today. So Amelia did her PhD here under the supervision of Michael Brown, so some of you might have met her. She then went to work as a postdoc at the University of Nottingham in the UK. She has now moved to Perth and work as a postdoctoral research associate in observational extragalactic astronomy at the University of Western Australia. And her research focuses on using integrography and spectroscopy from large galaxy surveys to study galaxy evolution and morphology. So a topic we'll learn more about today. And finally, it's also worth mentioning Amelia is a passionate campaigner for gender equality in astronomy. So please take it away, Amelia.
Great, thanks, Valentin. Let me share my screen. All right, can you see the whole thing?
Yes.
Beautiful. Right, hi everyone. Thank you so much for inviting me. I'm very excited to be back at Monash, even virtually for the day. As Valentin mentioned, I did spend 9 years of my life there, and there is a lot of names that I recognize in the participants list, many of whom taught me throughout my 9 years at Monash, and for that I can only apologize. So today I'm going to be talking about some work that I've been doing in my last two postdocs, so both at the University of Nottingham, and I've been here at ICRA UWA in Perth for the last year or so now. And as already mentioned, I'm going to be talking a lot about extragalactic science and integral field spectroscopy, but we'll go through it all together, hopefully. Before I get too far though, I thought it might be fun just to reminisce just a little bit from my time at Monash. So I was there for 9 years. I started my Eng-Sci degree in 2007. Then I did honours and then a PhD. So a few familiar faces, some of you that have been there for a while might notice. This is me graduating from honours in 2012 over in the maths building, back before MaNGA was a single entity. That's Dave Kinneborough there, some of you might remember. And this was my honours supervisor, Kevin Pimblett.
Just a sec. Is everyone
on your first slide?
Yeah, I think it's still your first slide, yeah.
Oh, no. Okay.
Mirroring or something?
Oh, you would think I would have understood Zoom by now after, you know, a year of using it. Right, how's that?
That's better.
Perfect.
Okay. Well, so this was Kevin, this is Dave, this is me. Let's fast forward to 2016 when I handed in my thesis. I don't know if the students still go to walk down to the graduate school, but that's what we used to do back in the day. So here I am with a whole bunch of students, and there's Michael, my PhD supervisor there, just before I handed in my thesis. And you'll see there's another tall gentleman also handed in his thesis on the same day. That was Jake Crossett. We stole each other's thunder by submitting our PhD thesis on the exact same day as each other. Right, but let's go back to some science, shall we? So the universe is dying, as I said in my abstract. It might seem like a bit of a morbid thing to say, but like I said, this is going to be a talk on galaxies. So when I say the universe is dying, I mean the galaxies are dying. And by that, I certainly mean that the star formation occurring in galaxies at current times is a lot less than it was back in the day. So galaxies are slowly settling into quiescence or quenching. You can use those two terms interchangeably. So I've got a plot to back this up. This is a very famous plot by Maddow and Dickinson, and it's just showing the cosmic star formation rate history of the universe. You can start all the way back here at redshift 8 or look back time of 13 odd gigayears, depending which way you want to look at it, and you can follow the star formation of the universe back in time all the way to today. Now I've already got a weird little symbol here, so we'll consider this the star formation rate density is what we're calling it. So it's just the amount of star formation rate that's happening at a certain time in the universe's history. You can see up here at about redshift 2 or 10 gigayear ago, we reached the peak of the cosmic star formation in the universe. So the universe is forming as many stars as it was ever going to form, and then we've slowly just headed on down all the way to current times now at zero, redshift 0 I should say, and the universe is forming far fewer stars than it was. Now we can see this if you just look at galaxies from these two epochs too. So these are a couple of galaxies from around redshift 2, and you can see a couple of things. They are very clumpy, they're very highly star forming, and they're very blue. Now it's important because we associate blue colors with star formation in galaxies. The reason for that is because these young stars, these really short-lived stars, so the O and the A-type stars, they emit a lot of light in the UV and also in the blue region of the optical spectrum. So that's why star-forming galaxies appear very blue. It's just because there's a lot of these young stars around. Now these stars have all died, lived their lives by the time we get to redshift 0 mostly. And of course I've cherry picked these two galaxies, but they are very red compared to these two galaxies over here. The reason that older galaxies are red is because, like I said, all of these young O and B type stars have died, leaving just those M and those really long-lived low mass stars. They emit much more of their light in the red, in the infrared region of the electromagnetic spectrum. Right, so universe is dying. But the question is, what is it that's actually killing galaxies? Or how to get away with cosmic murder? So here we have a nice star-forming galaxy here. We know it's star-forming because we see a lot of blue blobs, and these are the regions where the stars are being formed. Blue because they're the young stars, like I just said. So for star formation, the most important thing a galaxy needs is a supply of gas, and it's really good if this gas is cold. So you can think of this as the fuel for star formation. This usually comes in the form of hydrogen, and there's probably two main different types. You've got neutral hydrogen, H1, and you've got molecular hydrogen, or H2. So this is the good stuff, the H2. You can think of this as like the premium unleaded fuel, whereas the H1 is more the ethanol. It needs further refinement really before you can use it for star formation. So galaxy needs gas. If this gas supply is interrupted, then star formation can cease. Okay, and if you don't have any star formation, the galaxy quenches or dies. There's heaps of different ways that you can interrupt gas supply to a galaxy, but broadly you can put them into two categories. The first one being environmental mechanisms, which is a whole separate seminar. We're not going to talk about those today. The second is secular mechanisms, which usually mean internal mechanisms. This plot shows basically a whole bunch of different secular mechanisms or ways that you can stop gas getting into a galaxy and forming stars. It can be really simple. You can stop the gas flowing onto the galaxy in the first place, and that's going to cease your star formation. But if the gas does get onto the galaxy, it will be hot. And remember, I said you need cold gas for star formation. So you can also stop the gas from cooling. AGN are right here as well. That's also going to stop star formation. If your gas does cool, you can still stop it from forming stars by a whole bunch of different mechanisms here. And the two that I want to focus on today are these two here, morphological quenching and bark quenching. So we're going to investigate those as possible drivers of galaxy quenching today. If you do have cold gas and it is used, you can also consume it very quickly. If you use up all of your cold gas really quickly, there's nothing left for you to continue forming stars. And again, you will quench. And finally, you can also eject a lot of this gas that would otherwise have been used for star formation. And you can see again, AGN are implicated here as well. Right, so we need to start quantifying some of these pretty pictures in some way. So this is the star forming main sequence, or the SFMS plot, if I've abbreviated it anywhere in these slides. This is really important that you should pay attention to this plot because it's going to come up a lot in this seminar. So it's really simple. All it is just the measure of the stellar mass of a galaxy, and all that is just the number of existing stars that are already present in the galaxy, versus the star formation rate of a galaxy. So the number of stars that are forming in the galaxy right now. Now, the majority of galaxies follow this blue line, and we call this the main sequence, or the star forming main sequence. Most galaxies will live very happily along this line with a little bit of scatter. So in general, the more massive your galaxy is, the higher the star formation rate. Okay. But there are outliers. You have this class up here of starburst galaxies. They are forming more stars than you would expect for their stellar mass. And that's usually because there's something really weird happening to them, usually a merger or an interaction or something like that. You've got a bit of a green valley transitional region. And then down here, you have what we've called the red and dead galaxies region, or passive galaxies. These galaxies don't have as much star formation as you might expect for their stellar mass. So in general, we believe that a galaxy will live most of its life on the star-forming main sequence, and eventually, somehow, it will quench. Its gas might be removed, it might use it all up, but most galaxies will end up down here in this red and dead region. The one other thing of note I wanted to show you on this star-forming main sequence plot is actually at high stellar masses, the star-forming main sequence line bends. So at the highest masses, galaxies have not as high a star formation rate as you might expect. And there's a lot of reasons for that, and we're going to go into them today. Okay, hopefully that was all clear, because I promise you we're going to come back to this plot several times. Before we get any further though, I just want to talk about the constituents that make up your average galaxy. And today I'm talking just about disk galaxies, which do make up a very large fraction of the local universe. The other type of galaxy is sort of your spheroid or your elliptical galaxy. We're not talking about those today. So disk galaxies will generally have a disk, and I'm showing it face on and edge on. So the disk is extremely thin. So this disk is where your star formation occurs, and your stars will rotate nicely in the plane of this disk. Now the component that most disk galaxies have is a bulge. The bulge is a spheroidal component which is embedded in the center of the disk. The stars within the bulge are generally more on dispersion or random orbits, so the dispersion-dominated orbits, whereas the stars within the disk of the galaxy are very rotation-dominated. The final component that some local universe disk galaxies have is a stellar bar. And in fact, we think now that almost 2/3 of local universe disk galaxies possess a bar. So it is an important component to think about. The bar is a disk phenomenon. So it's made up of disk stars, all rotating, but on very highly elongated orbits. Because it's part of the disk, you won't see it when the galaxy is edge on, because the edge of the disk will be hiding the bar. So today I want to investigate bulges and bars as possible drivers of galaxy quenching. That's what we'll be talking about. First of all, let's start with bulges. So, do bulges kill galaxies? Here's a little bit of circumstantial evidence. 2 galaxies. The first one here on the left, NGC 3621, it's a beautiful star-forming galaxy. See all these little blue blobs? These are regions of star formation. But you'll also notice that it doesn't have much in the way of a central mass concentration or a bulge. In contrast, you've got M85 over here. This is a very bulge-dominated galaxy, very large central bulge region, and you'll notice it's red, which I said before is consistent with it being a quiescent galaxy. So just 2 galaxies here, but you might say it's very suspicious, the fact that the bulgeless galaxy is star-forming and the very bulge-dominated galaxy is quiescent. This is what makes us think that maybe bulges are involved in the quenching of galaxies. And in fact, we have, let's move that. We have some observational work showing this. Looking at the correlation between domination of bulges in galaxies and the star formation rate in galaxies. This is that same star forming main sequence plot I showed you earlier. So stellar mass on the x-axis and the star formation rate on the y-axis. Your main sequence line is shown here in white. You can see it starts to bend at high stellar masses. The bins in this plot are color-coded by the bulge to total ratio of a galaxy. Now, what's that? All it is just the fraction of light within a galaxy that comes from the bulge versus the rest, so the disk usually. So for example, this galaxy here has a small bulge, so its bulge to total ratio is quite low. This galaxy here has a very large dominant bulge, and I should say this is probably a little bit unphysical, but it has a very large bulge to total ratio, very high bulge to total ratio, almost 0.9. So we're going between 0 and 1. So what you can see is that on the star-forming main sequence, these galaxies are very disky or disk-dominated. They have very low bulge to total ratios. In contrast, down here in the passive region of this diagram, you'll notice all passive galaxies tend to be very bulge-dominated, have very high bulge to total ratios. So what that's telling us again is what I showed you in the previous plot, but with more galaxies this time, is that bulge-dominated galaxies are passive. So, how could bulges kill galaxies? Why do these bulge-dominated galaxies have these low star formation rates or are passive? So in my mind, there's kind of 2 different ways or different schools of thought in terms of bulges acting within galaxies to help quench them. The first one is this morphological quenching scenario, as made famous by Marie Martig in 2009. So that is, you have your galaxy, and your galaxy goes through repeated mergers throughout its lifetime. So not so many major mergers, but galaxies in general will have plenty of minor mergers. And every time these mergers come from whatever angle, they will puff up the central region of your galaxy, and they'll build a bulge. And I should say we're talking about a classical bulge here. So you're puffing up the central region of the galaxy, and through this bulge growth process, this actually stabilizes the disk against further star formation. So you'll remember earlier I said that we need cold gas for star formation, but you also need fragmentation. So there's people on this call that know much more about this than me, but as I understand it, you need to have some sort of instability to fragment your gas cloud and to initiate star formation. So if you've stabilized your disk against that, even though you have cold gas just sitting there, it can't form new stars. That's the concept of morphological quenching. The other option is a little bit simpler. It's just that you have a larger component of your galaxy that's not forming stars, which is still contributing to the stellar mass of the galaxy. So we don't see star formation occurring in bulges. We see it in the disks of galaxies. So if you build up a very large bulge, however you do that, it might be mergers, might be secular growth processes, come back to that. You build up your central component, you are adding to the stellar mass of the galaxy, but star formation is not occurring within this component. So you're adding to the mass of your galaxy, but you're not adding to the star formation rate of your galaxy. Hence your galaxy looks like it has a lower star formation rate than it should for its stellar mass. I hope that made sense. So in my mind, they're the two options in terms of methods or mechanisms in which bulges can kill galaxies. We chose to look at this from a kinematic standpoint. Okay, so everything I've been talking up to now has been photometric. So now we're going to move into spectroscopy and look at the kinematics of these galaxies. So first, I need to explain to you what I mean by kinematics. And for that, I need to explain integral field spectroscopy, which is the technique that I use in my work. So imagine you have this nice galaxy sitting here. This is a galaxy from the Sloan Digital Sky Survey. Now, the Sloan Digital Sky Survey took a spectrum in this very central region here, the very nuclear region of this galaxy. And the spectrum looked something like this. Now, if you don't stare at galaxy spectra all day, I can tell you that that is a star-forming spectrum there. One important thing to remember, I guess, is that galaxy spectra are just a whole bunch of stellar spectra stacked together. So what you can tell from galaxy spectra is about the stellar populations of the stars within the galaxy. You can tell how metal-rich or metal-poor the stars are. You can tell how old the stars are, all by the shape of the galaxy spectrum, because it just depends what combination of old young stars are in the spectrum. The additional part that you see in galaxy spectra that you don't see in stellar spectrum, though, are these emission lines. There's one here, and there's a whole bunch of big ones here. There's H alpha N2. These emission lines come from the interstellar medium, or the gas within the galaxy. So not only can we hear about the age and the metallicity of the stars within the galaxy, we also know about the chemical composition of the gas in the galaxy as well. So there is so much you can tell about the galaxy just from a single spectrum. But even better, okay, so this actually is the nuclear spectrum of this galaxy. So this tells us what's going on at the very core of this galaxy. What if instead we took spectra across the face of the galaxy? So all of these little fibers we've placed down within our field of view, and then you can get spectra at all these different regions across the galaxy. And what you get to see is how various properties of the galaxy change across the galaxy. And that's not particularly surprising. Of course, you would expect the central regions of the galaxy to be different to the outskirts. We have some spiral arms in here as well, which will be different to the interarm regions. And so that's integral field spectroscopy. It's looking at the galaxy as a whole. And what you can start to do is build up maps of various parameters. For example, you could make a H alpha map of this galaxy, which is going to tell you about where the recent star formation is occurring. The other thing that you can do is kinematics. And that's by taking the redshift of each of these spectra. So you find some individual lines, so maybe the H and K lines here, and you measure the wavelength of them, which is this axis here. the wavelength of them, and you compare that to the wavelength of these lines on Earth. Divide by the speed of light, and that gives you the redshift of that galaxy, or the recessional velocity. Now you can do this across the face of the galaxy, and what you'll get is ever so slight differences, and that's because the galaxy is rotating. And you get plots like this. So the only component of velocity we can measure is the line of sight velocity. So it's coming towards us in a way. We can't measure any tangential velocity, but that's enough to tell us about what's happening within the galaxy and how the stars are rotating, or the gas too, if we're interested in that. So you get plots or maps such as this one, and this is the line of sight velocity here. So you can imagine for this galaxy that the red region is maybe rotating away from you, whereas the blue region is rotating towards you. So it's just these tiny little differences and variations in sort of the redshift of these various spectra that tell you what's happening within the galaxy. So this particular galaxy, like I said, is rotating, which is not surprising whatsoever because it's a spiral galaxy. A spiral galaxy is a disk galaxy. Disk galaxies rotate, okay? But there is quite a bit you can get from these rotation maps. So, for example, this is the exact same galaxy as I showed you in the previous plot. And I was showing you that there was quite a bit of rotation occurring because you had these nice sort of blue, white, red rotation maps that show you very nice, even regimented rotation within this galaxy. The other type of galaxy you get is something like this guy over here. This galaxy, you can see from its velocity map, is fairly messy. There's no nice, obvious rotation occurring in this galaxy because the colors of this map are very disordered. So actually, the stars in this galaxy are on random orbits, and we call this a dispersion-dominated galaxy. It's dominated by random motions. So these are the two types of galaxies we see: these ones that are rotation-dominated, and those that are dispersion-dominated. Now, if you think back to Hubble's tuning fork, we can kind of remake that, and this is called the tuning comb now. So I guess you've got the comb handle, and then you've got the prongs of the comb, whatever you call that. Anyway, and you can see these slow rotators. So these galaxies that have stars that are on random orbits sit at the handle of this tuning comb. And we call them slow rotators, which is a bit of a misnomer because they don't really rotate at all. But if you think back to the Hubble, the classical Hubble classifications, you have these galaxies tend to be ellipticals. Okay. These fast rotators, which are these rotation-dominated systems over here, the stars are all in nice rotation-bound orbits within a disk. These galaxies will look like lenticulars or S-naughts or spirals of some form, and that's what these prongs are on this fork. So this is how we classify galaxies these days, or at least kinematically, into sort of fast rotating systems and slow rotating systems. The fast rotators, of course, being disk galaxies. So we need to quantify this somehow. As nice as it is staring at rotation velocity maps, which I do all the time anyway, but we do need a way of actually quantifying this. And we do that using this lambda r parameter. Now I promise you this is the only equation in this talk. I don't want to lose you all, and we can ignore that part of it. So this lambda r parameter, or we call it the spin parameter within a galaxy, all it is the ratio of line of sight velocity of the galaxy to the velocity dispersion of the galaxy. So you can think of it as the ratio of ordered motion in a galaxy to disordered motion. Okay. So for example, this value varies between 0 and 1. So a value close to 1 would mean that you have heaps of ordered motion and hardly any disordered motion. So your galaxy is basically a pure disk. In contrast, if your lambda r or your lambda r value was close to 0, you would have mostly disordered motion. So your galaxy would be sort of a spheroid like this guy over here. So galaxies like this, high lambda value, galaxies like this, low lambda value. The other thing that I need to mention is that this lambda parameter is correlated with the bulginess of the galaxy, or the degree of bulge dominance. The reason for that is because, like I was saying earlier, bulges are spheroid components and dispersion dominated. So if you have a disk galaxy with a giant bulge embedded within it, you're going to have, Ilya says, why does it make sense to weight by R rather than say M? Right, so R is the radius of the galaxy. We don't know the mass, I guess is the reason, right? We just have observations. we know the flux, so we know the amount of light, but unless you assume a mass to light ratio, it gets a little bit tricky. What we do know is the radius at which we're measuring these velocity values and these dispersion values. Right, so sorry, I should say this lambda r parameter is correlated with bulges. So a large bulge embedded within your disk is going to lower your lambda value because you have a large component in your galaxy that is dispersion dominated. So it's dragging down this lambda r value. So this will become important in just a second. Right, so we're back to our good old friend, the star-forming main sequence. I told you it would come up several times, so I hope you were paying attention in the beginning. These are some results that we published earlier this year. And this is looking at the star-forming main sequence of galaxies. But this time we're color coding by the spin parameter, so lambda. Now, this is the same plot as the previous one that I was showing you. So stellar mass is a function of star formation rate. And this green line here is our star-forming main sequence line. You can ignore this blue linear line. That was just what the referee wanted. So these boxes here are colored by lambda r. So these yellow and green colors are these dispersion-dominated galaxies. So random motions of stars, whereas these blue values up here are your disks, your pure disks. So it's interesting to compare this to the previous plot that I was showing you with bulge to total ratio over here. What you do see is along the star-forming main sequence in both of these plots, you do see minimum values. So these are galaxies that are disk dominated, so small bulge to total ratio. And in the kinematics, we see they're also very rotation dominated galaxies along our main sequence lines. Interestingly, in the passive region of this plot, we only see the really dispersion dominated galaxies at high stellar masses. So these are the galaxies that are really bulge dominated, probably bordering on spheroidal down here. But in this region, which is also passive, but just lower mass, we don't see that. These galaxies seem to have very similar lambda value, almost a little bit less to those that are on the main sequence. That's in contrast to this plot over here, which is the photometric values, which shows that for all stellar masses, these passive galaxies have very high bulge to total ratios. So that's an interesting difference between photometry and the kinematics that we derive from spectroscopy. I'm going to delve a little bit deeper into these results. And we get this confusing plot over here, which I'm going to talk you through. What we can do is you can divide this plot into five bins, of stellar mass. Ignore the low mass stuff because we don't have many galaxies there. And what we're interested in is the median lambda, so spin parameter value, both above the main sequence line and below the main sequence line. So we've come up with this parameter here, delta ms. That's just the distance from the main sequence line. And then if your positive value indicates that you're above the main sequence line, this green line, and a negative value indicates that you're below. So I've looked at these 5 different mass spins, and these are the results here. The colored line is just the value for each mass spin, and then all the other mass spins are behind it. So a few things to take from this plot. There is a lot in this plot. So I should say this dotted line here at 0 just corresponds to a galaxy being on the main sequence. These are the average values within each bin. So you can see on the star-forming main sequence, most galaxies at most masses have fairly high values of lambda r. So that tells us that most galaxies on the main sequence are these intrinsically flattened disks, exactly as we expect. Okay. Going above the main sequence is also quite interesting. This goes into the starburst region that I was talking about earlier. Now, quite a lot of previous work thinks that this might be where you are forming your bulges because there's a lot of mergers and interactions taking place. And that's the reason you're starbursting, and sort of through a compaction scenarios or these sorts of things, you can build up a bulge. If that was the case, what we would expect for most of these lines is that they would dip down again as the bulge component is dragging down your values of lambda r. We don't really see that. We do see it to a degree at the low mass, and the high mass we'll talk about in a minute. But on average, for most galaxies, we don't see this downturn in lambda r, which is telling us this is not where the bulges are forming. Below the main sequence is also very interesting. Again, for the majority of low mass galaxies, so anything below 10 to the 11 solar masses, you'll see that the lines are fairly flat at these lower stellar masses. The reason for that is, well, we don't know the reason for that. But what we think is we're not seeing any sort of bulge growth occurring below the main sequence. So these galaxies are becoming more passive. They're losing their star formation, but it doesn't seem to be as the result of classical bulge growth. Now that scenario is reversed at higher stellar masses, so anything above 10 to the 11 solar masses, and this is the highest mass bin down here. You can see that below this main sequence, you get a really sharp drop off in your lambda R value. And so what that's telling us is that these galaxies are probably growing these spheroidal bulges very quickly. And that seems to be corresponding, this bulge growth seems to be corresponding to a decrease in star formation rate in these galaxies. So it's kind of interesting. It almost seems like there's two different paths to galaxy quenching based on their stellar mass. These higher mass galaxies, they seem to be having quite a lot of bulge growth within them, whereas these lower mass galaxies are still becoming passive, but they don't seem to be growing their bulge in any way. So what does that tell us? It seems that we don't necessarily need classical bulge growth to quench star formation, especially at lower stellar masses. So if bulges are implicated in the quenching of galaxies, it seems to be only happening at high stellar masses. Okay. Right, so that's bulges. The other component I wanted to talk about today are stellar bars. Okay, are they also implicated in this quenching of galaxies? So that's a bar there, this sort of region here. So it's just we call it a non-axial symmetric structure, but it's just this long bar across your galaxy. Okay. And like I was saying earlier, they seem to be present in about 2/3 of local universe disk galaxies. So they are important to understand, and to understand what their effect is on their host galaxies, because we're seeing more and more of them. So 2 bits of circumstantial evidence for the fact that bars might be helping to quench galaxies too. So the bar fraction of passive spiral galaxies is very high. This is some work I did back at Monash in 2016. If you take a sample of spiral galaxies that are passive, so they have no star formation, but somehow they've retained their nice their nice spiral arms, the fraction of bars in this sample is 74%, which is very high. If you compare that to a matched sample of star-forming spirals, but the same stellar mass, the bar fraction is much lower, only 36%. But the group fraction of these galaxies, these passive spirals and these star-forming spirals, is very similar. So we don't suspect environmental causes as the reason why these passive spirals are passive. So maybe it's secular, maybe it's these bars. The second piece of circumstantial evidence for bars in helping quench galaxies is that the length of a bar within a galaxy is very correlated with the star formation rate of the galaxy. Now here we are back at our good old friend, the star-forming main sequence, stellar mass, star formation rate again. This time the star-forming main sequence line is straight, but don't judge me, we didn't know back then in 2020. This is a sample of barred galaxies. This is from the MaNGA Galaxy Survey. And we measured the length of the bar in physical units, so in kiloparsec, for all of these galaxies. And what you can see is that for the higher mass galaxies, the bar length is longer physically. That's not surprising, because the more massive your galaxy, probably the bigger it is. Bigger galaxy, bigger bar. What we need to do is scale this by some sort of photometric property. So we chose the effective radius, or half-light radius, and that's just the radius within which 50% of the light of the galaxy is within. If you scale these bar length measurements by the effective radius of the galaxy, you get this here on the right. So the exact same, but this time the bar length is scaled by the effective radius of the galaxy. And this scaled bar length shows that it's actually the passive galaxies, and this is the passive region down here, that have the highest scaled bar lengths. So these are the bars that take up the biggest fraction of the galaxy. Right, so this is 2 bits of circumstantial evidence. But the question is, okay, so if bars are killing galaxies, how do they do it? Well, it's by using up all of their gas, as you might have seen from the very first slide I showed you. What we think happens, and we see this in simulations and to an extent in observations, is we think that bars act as kind of a preferential highway to funnel gas into the central regions of galaxies. Also to the outskirts, but we don't care about that so much. So you funnel this gas preferentially straight along the bar into the center of the galaxy. Now, if there's an active AGN there, you can feed that AGN, But otherwise, this gas gets used up really quickly in some sort of a starburst. So if you've taken all of this gas from the disk, you really starve the disk of fuel for star formation. And once you've used up all of that gas in the center, the galaxy quenches because there's nothing else left. This is what we think is sort of the bar-driven quenching scenario. Ooh, sorry. Oh yeah, we see this in simulations too. I thought maybe I should put a slide on simulations here because there's a lot of simulators in the audience. We do see this in simulations too. So this is a simulation of a barred galaxy color-coded by the Mach number. And you can see at the leading edge of the bar, the Mach number is the highest as expected. And this is actually where we see the star formation occurring if it is within the bar, is at the leading edge. But you do need a very complicated mix of shear and turbulence to be the correct conditions to see the star formation within the bar. Most of it we see happen when the gas is deposited into the central regions. Right, okay. So we think that maybe bars are implicated in helping quench galaxies. Let's have a look at some barred galaxy properties compared to a very stringently matched comparison sample, and that's quite important. So if you take a sample of barred galaxies, so that's these three in the first column and these three in the second to right column, you can match them not just on stellar mass, because bar fraction depends also on galaxy morphology type. You can match them in morphology as well, and you end up with this sample of very, very similar galaxies, but without bars. And you can start comparing their properties, which is what we've done in this work. So here's four very similar plots. The x-axis is always star formation rate. Let's have a look at the top left. We're looking at the mean age of these barred galaxies compared to their matched sample. I'm so sorry, I really hope you can't hear the leaf blower out the front, but apparently it's gardening day at my apartment. If it does get annoying, let me know. So sorry, we've got the barred sample in red, these contours, and the matched sample in blue contours. What you can see is that on average, the barred galaxy sample is older. So the stellar populations, the stars within this galaxy, these galaxies are on average older than the mass matched sample. The same is true when you move to metallicity. The barred galaxies are also more metal rich. Generally, that means the stars are more evolved. They've had more generations, they've spat out more enriched metals, and the new generation of stars will suck those up. And they are more metal rich than within this matched sample of galaxies. Don't worry about the dust, but we also see this in the star formation rate. So these matched galaxies that are unbarred tend to have higher current star formation rates than the barred galaxies. We can look at this differently in terms of the star formation history of the galaxies. I don't want to go too much into what star formation history means, but you can imagine this is just a plot of a whole bunch of different galaxies. The barred galaxies are in maroon, and the matched galaxies, the unbarred galaxies, are in blue. And each of these curves is very heavily smoothed, but it shows you the star formation history of each individual galaxy. This is look back time, so this is a long time ago. This is today, and then this is just the star formation rate of the galaxy. These are very, very messy, obviously, so it might be good to look at the mean value. So the mean value of the barred galaxies is shown in this maroon color, and the mean value of the matched unbarred galaxies is shown in blue. Now, there doesn't look to be too much difference between the two, but it is a log scale on the x-axis. So the difference in the peak of the star formation rate is actually fairly significant between the two. And the other feature I'll also point out is we see this little kick up in star formation rate in the unbarred galaxies at current times that we don't see in the barred galaxies. So more recent star formation, as shown in the previous plot. You can measure a couple of things off this plot. For example, you could measure the time taken for a galaxy to reach 80% of its total mass. And all you have to do is integrate under these curves, like so, and you get a plot like the right. And you can see that on average, barred galaxies reach 80% of their total mass, their final mass, earlier than the unbarred galaxies. So the point I want to try and make here is that barred galaxies live fast and die young. They've done all of their evolving early on. So galaxies of the same mass, one barred, one unbarred. The barred galaxy has built up all of its mass much quicker than the unbarred galaxies. Which is exactly what you would expect if the barred galaxy with the bar was helping to quench the galaxy. It can't build up any mass at late times because the galaxy is already quenched. It's not forming new stars. So So the main point I wanted to make from this slide is that bars are linked to the early cessation of star formation in galaxies. We see both of these things. We see galaxies that have quenched early have bars, and barred galaxies quench their star formation early. But unfortunately, it's very difficult to separate which came first, the passive galaxy or the bar. It's one of those classic chicken or the egg problems. You have a nice galaxy like this one here on the right, nice barred passive galaxy. But the question is, did the bar help quench the galaxy? Was the galaxy happily star forming and then the bar formed, helped quench the galaxy? Or the flip side of that is it just that bars form more easily in passive disk galaxies? And simulations certainly show that. If you have a gas-rich disk and a gas-poor disk, and you simulate bar growth and all of that, by the end of the simulation, the bar within the passive disk is going to be much bigger and more advanced and more evolved than that in the gas-poor disk. So unfortunately, from our observations, it's impossible to tell which one came first. Certainly, a lot of the evidence points towards the fact that bars are involved in the quenching of galaxies, but unfortunately, we can't say for sure. It's not the end though. This is some recent work that's taking place with the timer survey. So future surveys are going to help, but what you need is to be able to resolve the very central regions of the galaxy. So these are the nuclear disk regions of the galaxy. And with that, you really need something like MUSE to get the spatial resolution required to resolve this. The reason this is so important is that the nuclear disk is built up by the bar within a galaxy. All the other stars within a bar are just taken up from the disk of the galaxy, so their stellar population properties are going to be really similar to the disk. The nuclear disk, though, is all new stars, which are built from the bar. So if we can age date this nuclear disk region, we can be able to date when the bar formed, whether it was ages ago or whether it was relatively recently after the galaxy quenched. And here's some examples of beautiful MUSE data, which I don't have access to, but other people do. This is a map of the age of the stellar populations within this pink box here. And you can see this nuclear disk here. You can see it, this little ring of younger stars. So these are all stars that formed when the bar formed as well. So we can age date the bar in this way. This is metallicity. This one here is alpha enhancement, which I won't go into. But what you can see is this kind of secondary bar in sort of perpendicular to the direction of the main bar. We call this a nuclear bar. This has only recently been discovered. So it seems that most bars have not just a nuclear disk, but also a nuclear bar within the bar. This is very much an area of active research. But the point I'm trying to make is that not all is lost. Hopefully within the next couple of years, we'll have more answers towards this particular topic. So I'm aware I've been rambling on for quite some time. So I think it's probably time that I finished up and took some questions. But just to summarize what I've been talking about, we've been thinking about what kills galaxies. And we've got two morphological drivers. First, bulges. So we know that bulge growth occurs to some degree while the galaxy is still star forming, so on the star forming main sequence. While this seems to be enough to quench high mass galaxies, it's not enough for low mass galaxies. So we think there might be some other mechanism happening here. So the bulge growth is not enough to quench galaxies, all galaxies. What about bars? We showed that bars are pretty much unequivocally linked to the early cessation of star formation in galaxies. But unfortunately, it's impossible to tell whether the bars are the ones that helped quench the galaxies, or it's just that they formed more easily in these passive disks. But there is still hope. Stay tuned for more MUSE results, I would say, resolving these nuclear disks. So I will stop talking now. Thank you all for listening. I hope the leaf blower wasn't as annoying for you as it was for me. And I will take any questions that you have.
Thanks for this great, very clear talk, Amelia. Please join me for an unmuted clap.
Unmuted.
Unmuted. Thanks. Is there any question for Amelia?
I have one.
Yeah, please go ahead, Rosemary.
I would have thought the huge asymmetry in the gravitational potential associated with the bar would have a big effect on the velocity dispersion in the disk and you know, influence whether or not stars. Well, I would imagine you'd need fairly low velocity dispersion to get collisions, cloud-cloud collisions and so on, to get stars to form. So that's sort of my immediate, dynamicist sort of reaction to it. A bar is a big brute mucking around with things. So there's that, but this idea of funneling the gas onto the central regions, the gas has to lose angular momentum, and I mean we understand how that works in protoplanetary disks, but I just wonder how, if the timescales are right for that to work. I mean, obviously simulations are showing that happening, but I'm just trying to think through, I guess the torques from the bar must affect that angular momentum.
You're absolutely right. So bars also transport angular momentum, I should have said, both inwards and outwards. So it's important. The angular momentum is also very important here. That is why, though, that actually the gas doesn't flow straight into the center, not directly, because like you said, the angular momentum wouldn't allow that. It actually gets caught up in these very highly elliptical orbits and then sort of slowly spirals its way into the central regions.
Yeah.
But that spiraling is still much quicker than if it was just sitting within the disk of the galaxy.
Well, yes, I think you put your finger on it there. The bar must induce eccentricity, the angular momentum, the torquing processes involved must force more elliptical orbits than otherwise and gets them in there, and then the orbits damp somehow, losing angular momentum. Yeah, anyway. It's a nice
that's
problem.
basically it. Yeah.
Yeah, okay.
I see another question by Michael. Let's go ahead.
Hi, Amelia. Great talk, and nice to see how things have built on some of the work we started some years ago during your thesis. One question I had was for the low mass galaxies that are being quenched but don't have the bulge growth, are we seeing the impact of environment there? Are we seeing objects that are in near groups or clusters?
Yeah, so that's a really good question. It's something that we're actively looking into right now. In terms of really, really high density environments like clusters, this work was mostly done with the MaNGA galaxy survey, which doesn't have any clusters in it, but there is certainly some SAMI galaxies in there too, which, so we have 4 SAMI clusters within here. I mean, we certainly know that low mass galaxies are probably more susceptible to being affected by the environment that they're within. So it probably is more likely that, well, I mean, if it's not a secular process, it's probably going to be an environmental process, right? So I certainly wouldn't be surprised if these low mass quenched galaxies, which are already kind of rare to begin with, right? Sort of, a quenched dwarf is not really something that you see particularly commonly. So I wouldn't be surprised if they were sitting in some sort of structure, maybe being pre-processed or something like that. But yeah, certainly we're looking into it. I don't have any answers for you at the moment, though, I'm afraid.
Looking forward to the paper.
Is there any other question? If not, I have one. So you showed a plot around the beginning of your talk showing red and dead galaxies versus main sequence galaxies. And I noticed there were much fewer points for the red and dead galaxies. I guess this means the quenching is happening on a short time scale, or is it just that the universe is not old enough? Or is it partly due to observational bias that it's harder to detect those faint and red galaxies?
Yeah, it's all of those things. I'm not qualified to be commenting on the timescales of quenching. That's a whole different subject. That was more of a schematic, though. I think my main point was that most galaxies, when they're star forming, will be on the star forming main sequence. When they fall off the star forming main sequence, what you might hear of like the red sequence or something like that, that is a much larger part of parameter space. So it's not this nice, well-defined sequence, nice like linear line of galaxies. They're all over the shop, but just in this passive region. So my inclination is just to say that there is still plenty of passive galaxies out there, especially at redshift 0. I think just that plot was a schematic, so I guess I don't know, maybe they got sick of drawing dots.
Okay, thanks. Is there any other question? Because it was a very clear talk, not many questions. So let us all thank Amelia again.